Hi, I'm Mike Crowley, and today at Fluid Mechanics I'm going to give an introduction to the Wanda software tool. Wanda is a software program for modeling pipeline systems. It's very good at doing steady state and transient flow analysis, particularly of long pipelines and long pipeline systems. Today I'll give an introduction to the user interface, and I'll show you how to build a model using Wanda. I'll build a model of two reservoirs connected with a pipeline with a valve between them, and I'll show you what happens when you close the valve when the flow is running, and you'll get a surge event or a water hammer event in the pipeline. I'll show you how to do this shortly at Fluid Mechanics. So this is the user interface you're presented with when you start. Here is the working area where you're actually going to build your model. Over here we have a palette of components which we'll build the model with, and here is a property window. Now within the palette of components or shapes you have various components. We have tanks, pumps, all the sort of basic sort of hydraulic components that you could want to use. Within Wanda, I'm not going to be going into this today, but they have other modules. They can do heat transfer, and basically if we click on the tab for that, then there's components for doing heat transfer, and they also have components for doing more sophisticated control systems. But we're going to be just dealing with the Wanda liquid components today. So we want to have two tanks. So the first thing we need to do is select a tank or a reservoir in this case. So we're going to just use two reservoirs at different heights, and we're going to connect them together. So we just drag and drop the reservoir into the working space. Now, as I said, we're going to have two reservoirs. So I'll just move that over a little bit. So I just click on another one, and I'm going to drag that over there. Now, what I'm going to do is have an undulating pipe, and in the middle of the pipe I'm going to have an air vent valve. So the next thing we need to do is select a pipe. So this is the pipe component here, and we'll drag this in. Now we'll be putting a profile in for that pipeline in a minute, and showing how it goes up and down over hills. But because, as I say, we want an air vent, we need to select two pipes, and between the two pipes we'll put the air vent. And this is down here we have an air vent, so I think it's that one there. As you hover over the components, it tells you what they are. So this is what we want. So this is the air vent, and we're going to need a valve at the end of the pipeline because we're going to do a simulation later on where we actually close the valve. So that's the valve that we're going to use. Okay, so they're the basic components. I think that's all we need to do this model. We now need to connect the components up. So we go over here to the connection, and this basically creates nodes between the various components, and we just connect them up. So I'll connect that to that pipe to that pipe. I mean, clearly it doesn't really matter too much where you put things on the sheet, on the thing. And we then connect up the air vent in between those two pipes there. I'll go back to that mode. So the first thing we need to do is set up the tank. So we'll set up that tank there, and I say tank, reservoir. As I said, there's a couple of different types of reservoir we can use. This is what we call an infinite area reservoir. So it doesn't matter how much fluid comes out of this reservoir, the level is always going to stay the same. There are other options. This is a tank with, so if I put that in, this has got a limited area. So effectively, as the fluid comes out of the tank, the level would start to drop. But just to keep things simple for the time being, we'll have an infinite area reservoir. So once we click on the component, you'll notice the property window comes alive and starts showing the options. Now this property window is used for putting in the parameters for that component, and after we've run the model, we'll be able to look at the results in this window as well. So most of the components we don't need to do anything, but the thing we do need to say is the height of the reservoir. So I'm going to just, for this particular example, put the height at 25 meters. Now we also need to set the heights at the nodes between the components, okay, and I'm going to set that at 25 meters. Actually, you might say, well, why are we setting that and the tank at 25 meters? We could have set that to a lower level. You know, the outlet could be at the bottom of the reservoir, but just to keep things simple, I'm going to set that to 25 meters too. Now we've got the pipes here and the valve. Now what we can do is some of the values are going to be the same for all of these three here. So we've got the two pipes and we've got the valve. I mean, as you click on the components, you'll see that different parameters come up. So there's the valve, there's the pipe. Okay, but one thing I know, so if I hold the shift key, I can select all three components together. And what you'll notice here is some of the components, some of the names are in red and some of them in black. And what it means is when it's in red, it means that the values between the different components is different. So I'm going to, sorry, what we're going to do is the thing that we have the same for all of them is the size. So I'm going to just say the diameter for those. And we'll just set it for this example to 150 millimeters. Okay. Now, if I set that to 150 millimeters, you'll notice straight away that that's only set it for that component there, and the number has come up red. That means that all the other components have got different values. So what you can do is you've got that selected. If you select that, it just copies it through to the other ones, which is what you want, which is what I wanted to do. Now, if I go back to just selecting the pipes next, for the pipes, I'm going to also set the wall roughness, and I'm going to set that to 1 millimeter. Okay. There are various ways of working out friction, and this uses the one I'm going to be using is the Darcy formula with Colbert White friction calculation. Now let's go back to this pipe. Well, actually what I'm going to do is going to put a profile in for the pipe. Okay, so if I wanted to, I could just set the length of the pipe and then it would just take the levels from the nose on either end, but I'm not going to do that. What I'm going to do is put a profile in. So this is length height. So then what happens is you can go down and we get a table, a profile table. Okay, and we can put the chainage in, and then we can put the actual length of the pipe in. So basically we're going to start off at this end of the pipe at 35 meters. So 0 chainage, and it's 35 meters. And then at just for this example, I'm going to say at 3,000 meters, we're going to go down to 0. I'll put enter, we'll come up with a new line, and then I'll put at 7,000 meters, and we're going to put in 10 meters in there. So basically the pipe starts off at 30 meters, drops down to 0, then comes back up to 10 meters. So what we need to do then is put on that node there, we just put in the level that we had for that, which is going to be 10 meters. We'll keep that the same. You can have it's different. And then for this pipe here, I'm just going to put in that the pipe length is, let me just, so we're going to go pipe length, it's going to be 6,000 meters. Okay, and the valve, I think we've set up most of the things we need for the valve. Yeah, we've got the diameter. Its initial position is 100%. In other words, it's opened. The other thing we need to set is this level here. So basically the level at this end of that pipe is 10 meters in the middle there. So that pipe is 10 meters at that end, and we're going to set it dropping down to 5 meters at that end. There, 5 meters. Okay, and that's also going to be 5 meters on the other end of the size of that valve. And I think we put in the head of that tank. No, we didn't. Head is 5 meters. So we've got a tank. In fact, what we can do is we can turn on some of the numbers. So that tells us that's at 5 meters, and I'll just put that up there, and that's at 25 meters, and it will come up, show you what the value is. But that's just by clicking on that tick box there. It just shows you on the chart. Got to be a bit careful. If you start putting too much of these down, you'll end up with a very cluttered screen. We're going to just initially run a steady state case, and what you can do is there's an option here, disuse. In other words, we can turn it off, and I'm just going to turn it off, yes. So you notice it goes a bit grayed out, so it's not connected. Okay, so we should now be in a position to run a sort of a steady state analysis on that model. So let's go. Often when you try to run the model first, there's always some error, but let's just see what happens. So I just first of all look at the fluids window. So this tells you the fluids property. Now the standard fluid they use is water, and that's exactly what I'm going to use. So I don't need to change any of these parameters here, but clearly you could put in various properties if you wanted to for different fluids, oils, etc. So model. Now the other thing I should perhaps point out is there's two modes of operation on this model. And the defaults when you first start a model is what they call engineering mode, okay? And this is what's sort of recommended to start a model off in. And basically this is just going to give you the steady state results. And it's easiest to run it in. There's less likely that you're going to get, there's less information needed, so the model's going to run. If you went to go for the transient case, you'd need to put all the transient information in and it wouldn't run. So we should be able to run the model now. So we go to calculate steady state. So value of wall. So I've obviously missed out something. Value of wall roughness is missing. So let's just go back to that component. And I thought I'd put that in already, but I hadn't. Obviously 1 millimeter. I'm sure I put it for that one. Yeah, that one's correct. So let's just calculate steady state. Okay, so I needed to set the characteristic for this valve. I'm going to set it to standard valve, and the type of valve is going to be a butterfly valve. So I think there might be other types, yes, but we're just going to use a butterfly valve for this case and diameter thing. So now let's just try and run that model. Calculate steady state. So it's asking me, do I want to save it? And I'll just say use that. So that little click there said that it's run the model, that little beep you heard. Okay, so if we look at some of these results, we can see the pressures at various nodes. And actually, so I just clicked on that node there, and the pressure there, if you look there, it's got a negative gauge pressure, so there's something not quite right with the model. I would have expected the pressure there to be around about 0 gauge. So I suspect I've probably done something not quite right. So we got that height there as 25 meters, and the tank is 25 meters. But let's just quickly look at the profile of the main. Yeah, I started that off at 30 meters. So in other words, the inlet to the pipe is higher than the tank, which is not quite right. So we'll put that to 25 meters. And now let's try running the model again. Okay. So if I click on that, yeah. So now I've clicked on there, the pressure there is 0, and you'd expect the pressure at this end as well to be 0. That's great. So that looks okay. So if we look at the profile, so what we can do is we can select a pipe, and we can look at the pressure profile along the pipe, which is this one here. And that's showing the pressure. So it starts off at 0 at the tank, increases as the level descends, and then as the level comes back up, the pressure decreases again. What's more useful, actually, a better way to look at it is we can select the two pipes, okay, and we can look at the pressure profile over the whole main, and that's what's happening. So basically, as the level goes down, the pressure goes up, and then at the end it comes down. Or alternatively, normally you look in terms of head. The red line there is showing you the profile of the main. Okay, so that's actually the level of the main. So initially it starts off at 25 meters, and if you remember the table we put in, it goes down to 0 meters at 3,000 meters along. It comes back where the air valve is up to at 7,000 meters up to 10, and then it goes back down to 5 at the end. So that's the profile of the main, and this is showing you the head, the total head along the main, as you'd expect. Because it's it's got a constant diameter pipe, it just decreases gradually to the end. So that's the steady state case, and of course you can look at the flow velocities in the pipe. So we can look at the velocity. Obviously the velocity in the pipe is going to be the same all the way along because it's just a steady state case, 0.36 meters per second, or it's probably got discharge flow rate. So actually this is the flow rate along the main, 23 cubic meters an hour. Before we go on to look at the transient case, we need to put in the air valve. Now looking at this, if we look at the pressure at this point here, the pressure is positive, so I don't think we're going to get any air coming in and out of that valve, but still we'll set up the air valve now, and we'll just say yes to that. So we do want to use it now. I'll just go through these air valves. Some of these terms are a bit not very obvious. So first of all, we need to get the level right. So it's 10 meters there. So we need to put the elevation of the air valves. So normally, actually, you might put the elevation of the air valve slightly higher than the pipe itself, because it will be above the ground and the pipe will be below it. But I'll just keep it the same. Laplace coefficient. When I first started using this software, I found this a bit confusing. What Laplace mean? What they really mean by this is the ratios of specific heat capacities. You know, the CP over, which is 1.4 for air. Okay. Ambient temperature, we'll just say 20 degrees. Inlet discharge coefficient. This is about how much the contraction as it goes through. I usually put 0.7 in and 0.7 for this as well. Inlet discharge area. Okay, so I'm just going to say that this is based on a sort of a 70 millimeter valve, and basically you need to put this in meters. Well, you could put it in millimeters squared, but I'm going to put it in meters squared, and it's I think it's 3850 e to the minus 6 meters squared. Okay, 3850. That's basically a 70 millimeter valve to the minus 6. Initial air volume. So this is the actual air volume that you've actually got in the valve when you start, and it's going to be 0. There's usually with these air valves some sort of residual volume left in there where the float goes, and I need to put a number in for that. So I need to put a volume for that, and I'm going to put in 0.1 meters. Okay. I think that's all the parameters we need for that. We'll just check that now that the model still runs before we move on to the steady state. Okay, so when I ran the model just then, I got an error signal. I've got two screens here, and on the other screen it's come up with the error. So it's just showing an error there. And just looking at this thing, so I think what's actually wrong is this elevation. It's elevation offset, not elevation. So what I should have said is the offset is 0. So we'll change that to 0. I think, yeah, that probably solved the problem. And let's just model run that again. Calculate steady. Oh yeah, and that worked okay now. So we can see the pressures and everything in there. But if we should actually look at the valve, if we look down here, the airflow is 0. Because there is no negative pressure. The pressure is positive at that point because it's a positive pressure. So now we're ready to go for the transient case. So we first of all need to swap over modes. So initially we were doing this engineering mode. We now need to go to transient mode. Okay, if these yes, okay. Now when we go to the transient mode, what you'll find is if we look at the model, there's more parameters to put in, particularly for the pipes. So we need to put in some information for the pipes, and the thing that we really need to do is first of all we need to set the mode that we're going to use, and we're going to talk about water hammer, or I always talk about surge. There's a number of ways you can model it. Water hammer is the proper way to do it. That's using what they call the method of characteristics to work out the water hammer. Wave speed. Now you can specify wave speed. I have done another video on how you actually calculate the wave speed in water hammer events, and it may be worth looking at that if you actually want to work out how to calculate it. you can actually put in the physical parameters of the wall thickness and that's actually what I showed you in the other video, how to calculate the wave speed. Or actually you can just specify what the wave speed is. I tend to prefer to just specify what the wave speed is, and we're going to set both pipes the same wave speed, and we're going to set it at a typical sort of wave speed for a plastic pipe would be about 1,200 meters a second. Actually, I haven't quite got that right. I set it for so 1,200 meters, but I need to obviously copy that across to the other one. Okay, and also that needs to be specified for both of them, so we're going to do it that way. Okay, so this uses a system called the method of characteristics to plot the progression of the wave speed, the wavefront going along the pipe. It basically breaks the pipe up into small sections, and we have what's known as a fixed step solver. So actually if we go up here, we need to change the time parameters. So what we need to do is the time step. So we can set how the shorter the time step we set, the more accurate the results are going to be. I'm going to set it to a time step of about 0.1. I think that's good enough for what we need here. And we can run the model for, say, 200 seconds of simulation time. There are other methods that other softwares use. I have given a demonstration on Simulation X and Modelica modeling. That uses a different way of modeling progression of waves along a pipe. It's not really as accurate as the method of characteristics. For long pipes, this is by far the most accurate method of using it. Other methods, basically what they do is split the pipe up again into small sections, which is what this does, but then they look at the bulk modulus of the sections, and actually the wave speed sort of propagates along the whole pipe almost instantaneously. So it doesn't quite give you the same characteristics. Definitely the method of characteristics for long pipes is by far the best. The reason why other software use a different method is because they use variable time step solvers. MATLAB, Simulink, SimHydraulics use that as well in their software. This does require fixed step time solver. Okay. So let's try running the model now and see what happens. Oh no, we need to, also what we're going to do here now is we're going to actually close the valve. So we've got a valve, we've got the position, and what we're going to do is we're going to set up a table of closing it over a period of time. Initial position is 100, use action table. That's what we're going to do. Yes. So action table. So at time 0, the valve is going to be 100% open, so we put 100% in there. Then at time 1 second, it's still going to be 100%. So initially, what I'm going to do is initially for the first 1 second, this will provide the steady state conditions that we want. And then what we'll say is over, say, a period of 20 seconds, we'll close the valve. We'll say 30 seconds to start with, and we'll go down to 0. And then at 200 seconds, which is the end of the run, it will still be 0. Okay, so that's going to give you a profile of the valve closing. So that's just come across the other screen. So effectively, that's what we've got. Going down to 0. Let's try running that and see what happens. So we're now going to do the transient case. So that has run, I think. And what we can do is we can, now if we click on the valve, we can look at the discharge. Now this will give us the discharge over time. So what you can see is the valve closing. Now actually, this is the flow rate through the valve. And I'll just show something else as well on this valve, the position. So this is showing you the position. And actually what we can do is we can bring the two graphs in together. If you click and drag it in, you bring the two in together. So the valve is closing, and actually what you find with a butterfly valve, which is typical, is that butterfly valves, they don't actually start to shut off the flow rate until you've got to quite close. So if I zoom into this zoom, if we zoom into this, say for the first 20, say 30 seconds, you'll find that it's only when you get to about 20 seconds, which is about, sorry, looking over this way, sort of when you get to about 25% closed, that the flow rate actually starts to drop off. Okay, close that down. So what happens? What's happening to the pressure? So we can look at that point there, and we can see the pressure. And this is a sort of a typical surge analysis of water hammer event. So as you close the valve, the pressure builds up, and actually it's on the second thing that you get the highest pressure in the system, and then it's slowly decays away over time. Let's just have a look at the whole pipeline. So we can click both of those pipes there, and we can actually look at the pressure through the whole pipe. Now what this tells you is this is giving you the maximum and minimum pressure over the whole pipeline. Okay, this is showing you the center line of the pipe, or the pressure for the center line of the pipe, and it's going up and down. This is the minimum pressure, that's the maximum pressure. Now it's perhaps a bit more useful to actually show what's happening in the transient case. So what you can do is we'll bring down this time navigator bar. Let's put it onto the screen. So I'll just bring it across, and this will allow you to see what's actually happening through things. So what we do is we press this start button, and it basically runs through the model, and it tells you what's actually happening. Ah, okay, so there we go. This is showing you the initial pressure. The blue line is the initial pressure in the pipeline, and as you can see, as the valve closes at the end, so let's just stop that for a second. So if we go back, we start again. So we're now up to 9 seconds and not much is happening. This is because the valve is just starting to close. Now we're getting to sort of 20 seconds and the valve is closing, and the pressure at the end of the pipe is starting to shoot up as it closes down. That pressure wave is then moving all the way along the pipe to the end. And it's sort of like at 40 seconds it's getting to the end. And now we can see what's happening over a period of time as the pressure waves fluctuate in the pipe. Okay, that's showing you what's happening. I'm going to speed it up a bit, and you can see the propagation of the wave. Over time that will start to die down, and eventually you'll get to the final condition, which is, well, that's not quite the final condition because I stopped it before it completely settled. But we can also look at the pressure at the point here, and that's the pressure at various points. Okay, so if I looked at that other plot and plotted out that various times, this is what we would get. Okay, so looking at the pressure here, this is showing you the pressure characteristic we've got for that valve closing. So let's see what we can do to try and smooth that out a little bit. So what I'm going to do is I'm going to freeze that screen, and when we make the changes, we can see what happens to it. Freeze all series. Okay, I'll just minimize that for a minute. Now we had a look at this valve, and as I said, the valve, as I showed previously, it didn't actually help reduce the flow until we got down to about 25%. So if we rapidly close the valve down to 25% and then do the rest of it slowly, I think that will help quite a bit. So what we'll do is I'll change this time. So if we say in 2 seconds it closes, so the first second it closes really rapidly down to 25%, and then if I put in that in 20 seconds it's now down to 0%, so it's actually going to close the last bit over a lot longer period of time, and then in 200 seconds it's down to, well, it's still at 0%. Okay, so that's what we're going to do. Let's bring back that sorry, let's just over here the graph. So if I bring back that graph and I'll run the model, calculate transient. Yes. Okay, so that's run. So if I now go back to this point here and I take those pressure and I put that onto that graph, right. Well, you can see it's obviously gone down, and the pressure's starting to rise a bit earlier because it's actually doing something useful at the start now, and because the pressure rise, because actually the closure is over a longer period of time, the actual effective closure is over a longer period of time, the surge pressures that rise have been reduced. And clearly, I mean, this is quite a long pipeline. So to have any sort of effect, I mean, this is it's got a length of 7,000 meters, and that one there is I forgot what we put down. Sorry, that pipe there, length is 7. So that's 13,000 meters. Excuse me, let me get a calculator. So if we have 13,000 meters, and we've got a wave speed of 1,200, so obviously that's going to be about 10.10 seconds. So 20 seconds is sort of basically the minimum that you would need to at 20 seconds you're still going to get significant surge, so we need to sort of increase the speed or increase the time to close for about 40 seconds, I think, to make any significant difference to this. So let's go back to the valve, put that to 40 seconds. Okay, let's rerun the model. Hopefully it should just put the model back in. So as you can see, it's starting to now smooth it out more, and we can just make one more effort on that. I mean, I think you need to 80 seconds would probably be about as good as you're going to get. So we'll try 80 seconds in there. So that's 80 seconds. Let's rerun the model. So I think that's about as good as you can get without using sort of surge or some sort of damping system in there. And if we look at the profile of the flow rate through there, you get it coming down nice and slowly. And if we look at the whole pipeline, now what's happening in the whole pipeline, the surge pressure should now be a lot less over the whole pipeline. So we're not going up as high as we were previously. So in summary, Wanda is an excellent program for doing surge analysis on long pipelines and pipeline systems. It uses the method of characteristics, which is proven to be the best method of solving surge analysis, particularly in long pipelines. If you have any general questions, then please leave a comment on my website blog, and I will endeavour to answer them there. I cannot answer any questions directly via email, but if you need more detailed advice or help on a surge, on a sort of consultancy type basis, then please contact me. My contact details are on my website. Please subscribe to my YouTube channel. I think there is a link above over there somewhere. And please like my video if you found it useful. Thank you for listening. That's it today for Fluid Mechanics. Bye-bye.